How often do you think about your heart health? Are you aware of the risks of cardiovascular disease? Well, let's dive into the heart of the matter. Cardiovascular diseases, encompassing coronary heart disease and stroke, claim the top spot as the leading cause of death in the United States. Particularly at risk are blacks and Hispanics in underserved communities. It's a sobering reality, isn't it? But there's good news. Cardiovascular disease is largely preventable. Stay tuned to learn how you can keep your heart beating strong. Heart Smarts, a health program, is here to empower you to live a heart-healthy lifestyle. This program is not just about information, but about transformation. It offers a comprehensive approach to help you understand and achieve heart health. Heart Smarts is committed to reducing the incidence of cardiovascular disease, the leading cause of death in the United States. The program focuses on underserved communities where the risk of heart disease and stroke is greatest. Through education and empowerment, Heart Smarts aims to turn the tide on these statistics. It's a call to action, a call to change, a call to live healthier, longer lives. Heart Smarts is about arming you with the knowledge and tools you need to make heart-smart choices every day. It's about the power of prevention and the promise of a healthier future. Remember, Heart Smarts is not just a program, it's a life-changing journey. It's about taking control of your health, one heartbeat at a time. But don't just take our word for it. Listen to these stories from people who have benefited from Heart Smarts. Imagine being told you're at risk for heart disease, a leading cause of death in the United States. Now picture having the knowledge and tools to combat that risk head-on. For people like Maria, a single mother from an underserved community, Heart Smarts was a beacon of hope. The program informed decisions about her heart health, ultimately reducing her risk of cardiovascular diseases. And then there's John, a middle-aged man who was once a prisoner of his poor lifestyle choices. For him, Heart Smarts was not just a program, but a lifesaver. It opened his eyes to the risks he was taking and gave him the push he needed to commit to a healthier lifestyle. These are not just testimonials, they are life-changing stories. Stories of empowerment, resilience, and triumph over heart disease. These are real stories from real people who have seen the impact of Heart Smarts in their lives. Are you ready to be the next success story? Your heart health is in your hands, and with Heart Smarts, you have the power to make a difference. It's time to take that first step towards a healthier lifestyle, a step that could redefine your future. Heart Smarts is not just an ally, it's a beacon, guiding you to make informed decisions for your heart health. So why wait? The path to a healthier heart is just a click away. You'll find the link to Heart Smarts right down in the description below. Start your journey towards a healthier heart today with Heart Smarts.
Ladies and gentlemen, esteemed guests, today, I stand before you to delve into the intricate world of engineering and physics that govern the creation and functionality of one of the oldest and most essential tools known to humanity, the knife. At first glance, a knife may appear as a simple instrument, but its design is a testament to the fusion of art and science. Let us embark on a journey through the engineering marvels and physical principles that shape the anatomy of a knife. The steel composition of a knife's blade is a critical aspect of its design. Engineers meticulously select alloys with specific properties, considering hardness, toughness, and corrosion resistance. The crystalline structure of the steel is manipulated during the forging process, aligning the molecules to enhance strength and edge retention. This metallurgical dance, guided by principles of materials science, results in a blade that can withstand the rigors of various cutting tasks. Consider the concept of stress and strain in the context of a knife's functionality. When a knife encounters resistance during a cut, the blade experiences stress. Engineers calculate and design the blade's thickness and curvature to distribute this stress optimally. This balance ensures that the blade remains resilient and minimizes the risk of deformation or failure, all while adhering to the principles of mechanical engineering. The physics of vibration and resonance also play a role in crafting a knife. When the blade makes contact with an object, vibrations are generated. Engineers strategically manipulate factors such as blade thickness and geometry to control these vibrations. This not only enhances the user's control but also influences the knife's acoustics, a subtle but significant aspect of the overall experience. The deployment mechanism of folding knives is a showcase of mechanical engineering ingenuity. Whether it's a traditional slip joint or a modern liner lock, the mechanism involves careful consideration of forces and levers. Engineers optimize these mechanisms to ensure smooth deployment while maintaining a secure lockup during use. The interplay of forces and materials in these mechanisms is a testament to the precise engineering required to balance functionality and safety. Beyond the blade, the handle's design involves biomechanics and material science. Engineers study the human hand's anatomy and the principles of ergonomics to create handles that provide comfort and control. The choice of materials, whether it be synthetic polymers or natural woods, is a result of careful consideration of factors like weight, durability, and thermal conductivity. A knife's seemingly straightforward design conceals a rich tapestry of engineering and physics. As we appreciate the elegance of a well-crafted blade, let us acknowledge the interdisciplinary efforts of engineers and physicists who, through a marriage of art and science, continue to refine and redefine the essence of this indispensable tool. The blade, as the paramount component of any knife, undergoes a detailed engineering process that begins with material selection. Engineers and blacksmiths meticulously consider the properties of various alloys, taking into account their hardness, toughness, and resistance to corrosion. High-carbon stainless steel has emerged as a favored choice due to its unique combination of attributes. Its elevated carbon content enhances hardness, providing the blade with an acute edge, while the stainless steel composition ensures resistance to rust and corrosion, crucial for maintaining the knife's longevity. Metallurgical expertise is further exemplified in the heat treatment process, the critical phase that defines the blade's mechanical properties. Through precise control of temperature and quenching rates, engineers manipulate the molecular structure of the steel. This results in a balanced blade that is not only hard enough to maintain sharpness but also exhibits the necessary toughness to withstand the stresses encountered during cutting. In the realm of physics, the blade's cutting edge becomes a focal point. The principles of edge geometry, specifically the angle at which the blade is sharpened, play a pivotal role. Engineers apply their knowledge of forces and materials to strike an optimal balance. A sharper edge facilitates easier penetration into materials, while a more obtuse edge provides enhanced durability. This interplay of physics and engineering in edge design is a delicate dance, ensuring that the knife performs optimally across a spectrum of cutting tasks. Consideration of the blade's mass distribution also involves principles of physics. Engineers meticulously shape the blade to achieve a center of mass that allows for precise control and maneuverability. The weight distribution affects the rotational dynamics of the knife during use, influencing factors such as stability and ease of handling. Furthermore, the physics of materials science comes into play when examining the microscopic features of the blade. Engineers delve into the realm of crystal structures and grain boundaries, seeking to refine the metal at the atomic level. This attention to detail enhances the blade's overall integrity, influencing its ability to resist wear, chipping, and deformation over time. In essence, the blade of a knife is a testament to the marriage of engineering ingenuity and the fundamental principles of physics. As we appreciate the beauty and functionality of these tools, let us also recognize the intricate dance of metallurgy, materials science, and mechanics that occurs within the heart of every knife, making it not just a utensil, but a masterpiece of scientific artistry. Continuing our exploration into the intricate realm of knife engineering, let's delve deeper into the physics governing the blade's shape and edge geometry. Engineers meticulously analyze the mechanical properties of materials to determine the optimal curvature and thickness of a blade. The blade's shape influences its strength, stability, and overall cutting performance. Consider the principles of stress and strain that physics introduces into the equation. A blade's geometry is engineered to distribute stress evenly along its structure, ensuring that it can withstand the forces encountered during cutting without succumbing to deformation. This careful consideration of mechanical principles is what allows a well-crafted knife to maintain its form and functionality over time. As we turn our attention to the honing of the blade, we enter the realm where physics becomes intimately entwined with the art of knife making. The honing process involves removing minute amounts of material from the blade to achieve a razor-sharp edge. Physics dictates the angle at which this honing occurs, with engineers employing principles of geometry to optimize the cutting efficiency. Physics also plays a pivotal role in understanding the interaction between the knife's edge and the material being cut. The blade's edge, when honed to perfection, reduces the contact area with the material, minimizing the force required to make a cut. This reduction in force is a manifestation of the principles of friction, where physics guides the knife's design to maximize efficiency and minimize wasted energy during cutting. However, achieving a fine edge is a delicate balancing act. Too thin an edge may compromise the knife's durability, as it becomes more susceptible to chipping or rolling. Engineers must navigate the trade-off between sharpness and robustness, using physics to strike the perfect equilibrium. This delicate balance showcases the marriage of scientific precision and practical functionality in the art of knife engineering. The blade's shape, edge geometry, and honing process are not arbitrary elements of knife design but rather carefully orchestrated applications of physics and engineering principles. As we wield these tools in our daily lives, let us appreciate the scientific ingenuity that has gone into crafting blades that seamlessly marry form and function, a testament to the enduring partnership between engineering and physics in the evolution of the humble knife. Consider the physics of force distribution. The handle serves as a lever, with the pivot point being the user's gripping hand. Engineers meticulously calculate the ergonomic design of the handle to ensure optimal force transmission from the hand to the blade. A well-designed handle not only enhances control but also minimizes user fatigue. Delving deeper into the physics of force distribution, the handle's design is a critical aspect that significantly influences the knife's performance. Engineers consider the principles of biomechanics, studying how the human hand naturally grasps and exerts force. The shape, contour, and materials of the handle are meticulously chosen to complement the anatomy of the hand, providing a comfortable and secure grip. Through careful calculations, engineers optimize the leverage effect, ensuring that the force applied by the user efficiently translates into cutting power. Considering the principles of mechanics, the handle is not merely a static component but an integral part of a dynamic system. Engineers apply principles of structural mechanics to evaluate the stress and strain experienced by the handle during use. This involves considerations of material strength, weight distribution, and the dynamic forces generated during cutting motions. A well-engineered handle not only withstands these forces but also contributes to the overall balance of the knife, enhancing its maneuverability and usability. The material properties of the handle also play a vital role in the physics of force distribution. Engineers carefully select materials that offer an optimal balance between strength, weight, and durability. Modern materials such as high-strength polymers, composite materials, or even exotic woods are chosen for their ability to withstand repeated stresses without compromising on comfort. This intricate material selection process reflects the fusion of materials science and engineering principles to create handles that stand up to the rigors of real-world use. Moreover, the handle design is not only about force transmission but also about minimizing vibrations and shock absorption. Engineers employ principles of mechanical damping to reduce the impact forces transmitted to the user's hand during cutting. This not only enhances user comfort but also contributes to the longevity of the knife by minimizing the wear and tear on both the blade and the handle. In essence, the physics of force distribution in knife design involves a sophisticated interplay of biomechanics, structural mechanics, and material science, the art of engineering a handle that seamlessly integrates with a human hand. optimizes force transfer, and minimizes user fatigue is a testament to the dedication and expertise of those who craft these indispensable tools. As we appreciate the elegance of a well-designed knife handle, we also recognize the profound impact that engineering and physics have on elevating the functionality and efficiency of this age-old instrument. Furthermore, the physics of friction plays a pivotal role in the performance of a knife. The interaction between the blade and the material being cut involves complex frictional forces. Engineers take into account the coefficient of friction, material properties, and the cutting motion to optimize the blade's performance. Reduced friction ensures smoother cutting and prolonged edge retention. Moving beyond the broad strokes of friction, let us delve deeper into the intricate physics that govern this essential aspect of knife performance. Engineers pay meticulous attention to the coefficient of friction, a dimensionless quantity that characterizes the interaction between two materials in contact. By selecting materials with specific coefficients, they can fine-tune the frictional forces at play during cutting. Material properties, such as hardness and surface finish, are also critical considerations. The interaction between the blade and the material being cut is akin to a microscopic battle, where the surface roughness and hardness of both materials determine the effectiveness of the cut. Engineers analyze these properties to optimize the blade's design, ensuring it is tailored to excel in specific cutting applications. The cutting motion itself is a ballet of physics in action. Different cutting techniques, whether it be slicing, chopping, or dicing, generate distinct forces and stresses on the blade. Engineers employ principles of mechanics to study these dynamic forces and design blades that can withstand the rigors of various cutting styles. The goal is not only to create a sharp and durable edge but also to enhance the knife's versatility across different culinary or practical applications. Reducing friction is not solely about creating a smoother cutting experience, it also plays a crucial role in edge retention. Friction generates heat, and excessive heat can compromise the hardness of the blade. Engineers must strike a delicate balance to minimize friction-induced heat during cutting. This delicate equilibrium involves the selection of appropriate materials, optimal edge geometries, and, in some cases, incorporating features like non-stick coatings to mitigate friction and heat buildup. Consider also the microscopic landscape of the blade's edge. Engineers leverage principles of tribology, the science of interacting surfaces and relative motion, to understand the wear and tear on the blade during use. This understanding informs the design of blade profiles, bevel angles, and edge geometries to maximize the knife's lifespan. In the quest for prolonged edge retention, engineers explore advanced surface treatments and coatings. Techniques like cryogenic tempering and nitriding alter the surface properties of the blade on a molecular level, enhancing its resistance to wear and corrosion. These processes are rooted in the principles of materials science, where engineers manipulate the microstructure of the steel to achieve desired mechanical properties. In essence, the optimization of a knife's performance involves a symphony of physics and engineering, from the macroscopic considerations of material selection and handle design to the microscopic realm of frictional forces and edge geometry. Every aspect is a testament to the marriage of science and craftsmanship. As we appreciate the elegance of a well-designed knife, let us marvel at the invisible forces and scientific ingenuity that make it a true work of art. Let's not forget about the physics behind the heat treatment process. Achieving the right balance of hardness and toughness involves precise control over the heating and cooling cycles. Engineers employ principles of thermodynamics to transform the molecular structure of the steel, ensuring the blade's ability to withstand stress and deformation. Delving deeper into the realm of heat treatment, the process is a sophisticated dance with temperature and time. Engineers meticulously orchestrate the heating phase, often subjecting the blade to extreme temperatures, sometimes exceeding 1,800 degrees Fahrenheit. This elevated temperature allows for the steel's molecular structure to transition into a more malleable state, making it receptive to subsequent manipulation. The critical phase lies in the quenching process, where the red-hot blade is rapidly cooled. Here, the laws of thermodynamics govern the transformation of the steel from austenite to martensite, a phase with increased hardness. The rapid cooling is typically achieved through immersion in oil, water, or other quenching mediums, and the selection of the quenching medium itself involves a careful balance to avoid excessive stresses that might lead to cracks or warping. However, the pursuit of hardness is not without its challenges. The hardened steel, while resilient, can also become brittle. This is where the delicate equilibrium between hardness and toughness comes into play. Engineers must strike a balance, often through tempering, a controlled reheating process. By carefully raising the temperature, they induce a controlled softening of the steel, enhancing its toughness without sacrificing too much of its hardness. Consider the phase transformations during tempering as a symphony of thermodynamic principles. The diffusion of carbon within the steel matrix at elevated temperatures influences its mechanical properties, resulting in a blade that possesses both the hardness required for sharpness and the toughness needed to withstand the rigors of cutting. Moreover, the application of stress-relieving techniques after the heat treatment is another aspect of engineering precision. Blades are often subjected to controlled deformation and subsequent annealing, aligning the crystalline structure and reducing internal stresses. This meticulous process ensures that the blade not only meets the desired hardness criteria but also exhibits enhanced resilience against fatigue and deformation during use. In essence, the heat treatment of knife blades is a fascinating marriage of physics and engineering, where principles of thermodynamics, metallurgy, and materials science converge. Each step in this process is a testament to the dedication of engineers who seek to extract the optimal performance from a simple piece of steel, transforming it into a refined tool that stands as a testament to the advancements in both science and craftsmanship. Delving deeper into the realm of materials science, the choice of alloy composition and crafting a knife blade is a meticulous process. Engineers consider not only the type of steel but also the specific alloys mixed in precise proportions. This blend influences the blade's hardness, corrosion resistance, and overall performance. The crystal lattice structure formed during the cooling process, a phenomenon rooted in metallurgical physics, contributes significantly to the blade's final properties. Mechanical engineering principles are crucial in understanding the dynamic forces at play during knife usage. As a blade encounters resistance while cutting, forces are distributed unevenly across the edge. Engineers analyze stress points, employing concepts of material strength and deformation to design blades that withstand these forces without failure. The geometry of the blade and the angle of the cutting edge are finely tuned to optimize cutting efficiency while minimizing the risk of fractures or deformation. Consider the intricacies of heat transfer and thermodynamics in the quenching process. Achieving the desired hardness involves subjecting the blade to carefully controlled temperatures, followed by rapid cooling. Thermodynamic principles guide engineers in manipulating heat gradients to create a blade with a hardened edge and a more flexible spine. This delicate balance ensures the blade's resilience and sharpness, emphasizing the intricate dance between thermal energy and material properties. Examining the handle design from an engineering perspective reveals a symphony of ergonomics and biomechanics. Engineers leverage principles of human factors engineering to create handles that maximize user comfort and control. Understanding the biomechanics of the human hand and the distribution of forces during various cutting motions allows for the development of handles that reduce strain on the user, enhancing the overall usability and safety of the knife. Furthermore, the physics of blade vibrations and resonance during cutting play a role in optimizing performance. Engineers analyze the natural frequencies of the blade, considering factors like thickness, length, and mass distribution. This knowledge aids in designing blades that minimize vibrations, resulting in smoother cutting experiences and improved overall user satisfaction. In conclusion, the world of knives is a fascinating intersection of various scientific disciplines. The harmonious blend of materials science, mechanics, thermodynamics, metallurgy, and human factors engineering results in tools that transcend their utilitarian purpose to become works of functional art. As we celebrate the craftsmanship of knives, let us not forget the dedicated engineers and physicists who continuously innovate and refine the very essence of these indispensable tools, shaping the cutting edge of technology and tradition.